What's going on, guys? Justin here, and welcome back to our 17th example video following our course on proofwriting. Now, today's example video is going to be centered on equivalence relations and equivalence classes, so let's go ahead and look at this first example. So this example says we're going to define a relation R on R2 by the following, where A comma B is related to C comma D if and only if A is equal to C. So first we want to show that this is an equivalence relation, and then we just want to describe the equivalence classes. So in order to prove something is an equivalence relation, we have to prove that it is reflexive, symmetric, and transitive. So let's go ahead and start with reflexivity here. So go ahead and write that out. Now this one is pretty self-evident. It's pretty easy to see that AB will be related to AB, as we have that A is equal to A. Okay, great. So let's get into our next thing that we need to prove, which will be symmetry. So I'll go ahead and write that out. So let's suppose that we have that AB is related to CD. Well, that means that A is equal to C, but we can just flip that using our regular equality rules to show that C is equal to A, which completes our symmetry proof, because now that we have our C on the left-hand side, we can write this as CD is related to AB. Okay, great. So now let's prove transitivity. So for transitivity, we are going to suppose that we have the following relationships. We have that AB is related to CD, and that CD is related to EF. Well, what does that mean? That means that A is equal to C, and C is equal to E. But that means by the regular transitive property that we have A is equal to E, which means that AB is related to EF. Great. So that finishes this proof off, that this is in fact an equivalence relation, and now we want to describe the equivalence classes. But we want to notice that these are related in the following way, where we have A is equal to C. So we can describe our equivalence classes as a series of vertical lines sharing the same x value, where each equivalence class is a different line. Okay, so that finishes this example off. Let's go ahead and get into the next one. Okay, so this one says we're going to define a relation R on the set of polynomials with real coefficients by P of x is related to Q of x if and only if P double prime of x is equal to Q double prime of x. We want to show that this is an equivalence relation and describe the equivalence classes. So let's begin with reflexivity here. So it's easy to see that P of x will be related to P of x because P double prime of x is by definition equal to P double prime of x. So that's kind of a trivial proof for reflexivity here. Next, let's do symmetry. This will go similarly to our last proof for symmetry. We're going to suppose that P of x is related to Q of x, but that means that P double prime of x is equal to Q double prime of x. And we can flip that so that we have Q double prime of x is equal to P double prime of x, which means that Q of x is related to P of x. Great. So now let's do transitivity. So for transitivity, we're going to suppose that we have the following relationships. We have f of x is related to P of x, and P of x is related to Q of x. Then that means we have the following relationships. We have that f double prime of x is equal to P double prime of x, and P double prime of x is equal to Q double prime of x. And we can see that that shows that f double prime of x is equal to Q double prime of x, which of course means that f of x is related to Q of x. Great. So that finishes the proof for proving R is an equivalence relation. So now let's describe the equivalence classes. So we can see that our equivalence classes will be all polynomials that share the same second derivative, but we can partition that into a few different cases. So for the first one, we will have 0th and 1st degree polynomials. And when you take the second derivative of those, you will just get 0. Our next class will be second degree polynomials. And these will only share the same second derivative if the leading coefficient of our second degree is the same. So with same leading coefficient. And lastly, we'll have 2 plus nth degree polynomials. And those will also need to have the same leading coefficients all the way down to our second degree term. So I'll just write with same leading coefficients as well. And I'll just say verbally that that is up to our second degree term. Okay, great. So let's go on to our next example. Okay, so this one says, suppose R and S are equivalence classes on a set A, and we want to show that R intersect S is an equivalence class on A, and then briefly discuss R union S. So to begin this, we'll do just like we've been doing and prove reflexivity. So we're going to do these proofs by using the fact that R and S are both equivalence classes on the same set A. So let's suppose we have some element X in A. But by the definition of R and S being equivalence classes, that means that we have X is related to X by R, and X is related to X by S. But that means that we have the following. We have that X comma X is in R, and X comma X is in S. But if it's in R and S, that means that X is in R intersect S. Great. So that finishes off our proof for reflexivity here. So let's do symmetry. So for symmetry, we are going to suppose that XY is in R intersect S. But by definition of intersection, that means X comma Y is in R and XY is in S. But because R and S are both equivalence classes on A, that means we can use their own symmetry property, which means that YX will be in R and YX will be also in S. But since it's in R and S, that means we must have YX is in R intersect S, which completes our symmetry proof. So let's go ahead and get into transitivity. So let's suppose that we have X and Y and YZ in the intersection of R and S. And then we want to show that XZ will be in the intersection as well. So let's split this up using the definition of intersection. So that means that we'll have XY and YZ in R. But we know that R is already transitive, so that means that we will have XZ in R. And we can use the same logic for S. That will give us that XY and YZ are in S. And by the inherent transitivity of S, that means that XZ will be in S. And by definition of the intersection, that means that XZ will be in the intersection of R and S. Great. So we've proved reflexivity, transitivity, and symmetry, which means we have proved that this is an equivalence class on A. So next we just want to talk about R union S. So I'll go ahead and write that down. We're going to consider R union S, and this will actually fail transitivity. So let me show you how that fails transitivity. So we're going to suppose that A is equal to 1, 2, and 3, and that we have R in S defined in the following way. So R will be equal to 1, 1, 2, 2, 3, 3, 1, 2, and 2, 1. And then S will be equal to 1, 1, 2, 2, 3, 3, and 2, 3, and 3, 2. Great. So we can see that this will fail transitivity, as if we union R and S together, we will have 1, 2, and 2, 3, but we do not have 1, 3. So that is a very quick counterexample to show that R union S will fail transitivity and thus cannot be an equivalence class on A. So let's go ahead and get into the next problem. So this one says let A equal the set A, B, C, D, and E, and we want to suppose that R is an equivalence relation on A, and then we want to suppose also that A is related to D, B is related to C, E is related to A, and C is related to E. How many equivalence classes does R have? So let's go ahead and write down what we've been given here for our relationships. So that we know that A is related to D, B is related to C, E is related to A, and C is related to E. And we know that R is an equivalence relation. So in order to figure out how many equivalence classes R has, let's go ahead and figure out how many things are related to each other by what we've been given here. So I'll just start by getting A related to as many things as we can. So we already know that A is related to D, as we've been given that, and we know that E is related to A, but because this is an equivalence relation, that means A is also related to E. But we have that C is related to E, so by transitivity we know that A must be related to C. I guess by symmetry and transitivity. But if A is related to C, we know that B is related to C, which means that A is related to B. But now we have that A is related to everything. Because R is already an equivalence relation, we already know that A must be related to itself. But if A is related to everything, that means by transitivity we can prove that all of these are related to everything. So we can see that B is related to C, and B is related to A, but A is related to D. So we can write that B is related to D, etc., etc. So that means we have this fact, we have they are all related to each other. But if they're all related to each other, that means that R has one equivalence class. So that takes care of the first part of the question, and we want to know, can we write out R as a set? And we can. I'm not going to write everything that's in R, but you can see how we would go about this. So we'll have AA, AB, AC, AD, and AE. And then for the next row we could write BB, BA, BC, BD, and BE, etc. all the way down to ED, where R is filled with every possible combination of these. So that's how we would write out R as a set. So that finishes this problem off, so let's go ahead and get into the next one. So this one says there are 5 different equivalence relations on the set A, which is equal to A, B, and C, and we want to describe them all by using diagrams. So let me go ahead by numbering these 5 diagrams and drawing out our A, B, and C for them. Okay, great. So there are our 5 diagrams. So let's begin with the most trivial of equivalence relations on A, which will be when each element is related only to itself. And we can see that we obviously have reflexivity there, but we also have symmetry, and we have transitivity as well. So for our next 3, we will have where every element is related to itself, but also we have 2 elements that are related to each other both ways. So to start, for number 2, let's do the one where all elements are related to themselves, and A is related to B, and B is also related to A. Then for number 3, let's do the same thing, but where B is related to C, and C is related to B. So they're all related to each other, but B is related to C, and C is also related to B. And then for the 4th one, we will have the same thing, but when A is related to C, and C is related to A. So they're all related to themselves. Then we have AC and CA. Great. Now for the last one, we'll just have where they're all related to themselves, and each one of the pairs is related to each other both ways. That's our last possible combination. So A is related to itself, B is related to itself, C is related to itself. Then we have A is related to B, B is related to A, B is related to C, and C is related to B. Then lastly, we'll have A is related to C, and C is related to A. So those are our 5 different equivalence relations on our set A, which is just A, B, and C. Great. So let's go ahead and get into our next one. So for this one, we've defined a relation R on the integers by x is related to y if and only if 5 divides 2x plus 3y. We're going to show that R is an equivalence relation and then describe its equivalence classes. So as we've been doing, let's begin by proving reflexivity. So let's suppose that x is related to x, and then we want to show that 2x plus 3x is divisible by 5, but that's pretty self-evident. We can see that 5 will in fact divide 5x. So that proves our reflexivity here. Next, we're going to do symmetry. So we're going to suppose that we have x is related to y, but that means that 5 divides 2x plus 3y. But if 5 divides 2x plus 3y, that means we can write it in the following way. 2x plus 3y is equal to 5 times a for some integer a. Next, we are going to subtract 5x plus 5y from both sides. So we can see if we do that, we will get 3 times negative x plus 2 times negative y is equal to 5, and that will be times a minus x minus y. And then we could simply divide through by negative 1 to get 3x plus 2y is divisible by 5. So that completes our proof for symmetry here. So let's go ahead and prove transitivity. So let's begin by supposing that x is related to y and y is related to z. That means we have the following, that 5 will divide 2x plus 3y, which means, of course, that we can write this as 2x plus 3y is equal to 5a for some integer a. And we have also that 5 will divide 2y plus 3z, where 2y plus 3z is equal to 5b for some integer b. Great. And so we want to show that 2x plus 3z will be divisible by 3. And so to do this, let's add these two equations together. So once we add them, we will have 2x plus 5y plus 3z is equal to 5a plus 5b. We can see that we can subtract that 5y over, and we will get that 2x plus 3z is equal to 5 times a plus b minus y. So thus we have proved that 2x plus 3z is divisible by 5. Great, so that completes our proof of transitivity off. So now we want to describe the equivalence classes of this relation R. And I'm going to tell you that the equivalence classes will simplify to the ones where x is congruent to y mod 5. So if you want, you can figure out why that is and then maybe post it in the comments. Okay, so let's get into our last example. So for this one, we have the following definition for R. So we're going to suppose that R is a reflexive and symmetric relation on a finite set A, and we want to define a relation S on A by declaring that x is related to y if and only if, for some natural number n, there are elements x1 through xn in A satisfying that x is related to x1, x1 is related to x2, all the way up to xn minus 1 is related to x sub n, and that x sub n is related to y. We want to show that S is an equivalence relation and that R is a subset of S. Then lastly, we want to prove that S is the unique smallest equivalence relation on A containing R. Now I'm not going to be doing the uniqueness and minimality proofs here in this video because I think this problem is already long enough as it is, so if you want to do those on your own for homework, maybe post them in the comments. So to begin, we want to prove that S is an equivalence relation. So let's begin by proving reflexivity. So we're going to begin by supposing that we have x, which is an element in A. Then there exists a little n, which is equal to 1, which is of course a natural number, and x1 is equal to x, which is in A, such that x is related to x, and x1 is related to x. So basically what we're doing here is choosing n to be equal to 1, so our string of relations starts and ends with x is related to x1. And then we have also that x1 is equal to x, so we have proved that x is related to x. So now let's do our proof of symmetry. So for this one, we're going to begin by letting x be related to y by s. Then we can use our definition for s. So then for some n, which is a natural number, there are x's 1 through n, which are in A, such that x is related to x1, all the way up to x1 is related to x2, all the way up to xn minus 1 is related to xn. And also that xn is related to xy. Now we already know from definition that R is symmetric. So that means that we can flip all of these string of equivalences in the following way. So I'll go ahead and write that out. We have that R is symmetric. So that means we can write our string of equivalences this way, where we have y is related to x sub n, and x sub n is related to x sub n minus 1, all the way down to x sub 1 is related to x. That's exactly the definition of what it means for y to be related to x by s. So then we have that y is related to x by s. Great. So now let's do transitivity. So just like we always do, we're going to begin by supposing that we have x related to y by s and y is related to z by s. Then we know we have some m and n, which are natural numbers, such that we have the following x sub n and y sub m. So such that there are x sub 1 all the way up to x sub n, which is in A, and y sub 1 all the way up to y sub m, which are also in A. And those are going to satisfy our relationship definition from above. So for x's, we have x is related to x1, x1 is related to x2, all the way up to x sub n minus 1 is related to x sub n, and x sub n is related to y. And then for our y's, we'll have that y is related to y sub 1, y1 is related to y sub 2, all the way up to y sub m minus 1 is related to y sub m, and y sub m is related to z. Okay, great. So for here, we are going to, for all I from 1 to n, we're going to put zi equal to xi. And for all I from n plus 1 to n plus m, we are going to put z sub I equal to y sub I minus n. So once we do all that, we'll see that we have the following. So then we have the following. So we'll have x is related to z1, z1 is related to z2, and that'll go all the way up to zn minus 1 is related to zn. And then we'll continue to count up. So we'll have zn is related to zn plus 1, and that will go all the way up to z sub n plus m minus 1 is related to y, and thus by our definition of s, so thus we have that x is related to z by s. And so for the very last part of what we're going to do here today, we want to prove that R is a subset of S. So to prove that R is a subset of S, we're going to suppose that x is related to y by r. So then there exists n equal to 1, which is of course a natural number, and x is equal to x1, which is in A, such that x is related to x1 by the reflexivity of r, and so x1 is related to y, which of course means that x is related by s to y. Thus we have proved that R is a subset of S. Great. So like I said, if you want to do this last part here where we prove that S is a unique smallest equivalence relation on A containing R, you can go ahead and do that for homework, but as far as this video is concerned, I think that's a good place to stop.